All right, welcome everybody. This is going to be the beginning of Unit 8 about right triangle trigonometry. Just a quick overview here. Trigonometry is going to be a tool that we use in order to solve for parts of right triangles. It's based on ideas of similarity. So there'll be some connections to what we did last unit. So let's go ahead and read this first part here. The angle-angle similarity postulate guarantees that all right triangles that share another acute angle, so right angle and an acute angle, will be similar. For example, you can see that all of these three triangles here on the right, we have all three of these triangles have a right angle, and they also have a 32-degree angle. Therefore, they will be similar to each other. Let's go ahead and write out some similarity statements. I'll start with this top one. So I'll call this one DEF. So DEF. D was the 32-degree angle, E was the right angle, and then F was the remaining angle. So that'll be XYZ, following the same corresponding order, right? 32, 90, and then the remaining angle, and then A, B, C. All of these are going to be similar. And similarity allows us to know that any ratios that we create using corresponding sides will have to be equivalent. That's the main idea of similarity that we spent last unit talking about. So for instance, if we pick two sides in one of these triangles, let's just talk about, I don't know, this side, the opposite side, the side that's going to be across from an angle, and one other one. If we write ratios of these sides, they will be equivalent. That's what similarity guarantees us, right? And also in this triangle as well, right? All of these ratios, whatever they would happen to be, obviously I don't know the particular side length measurements, but if we write ratios of these sides, they will all be equivalent. So what I'm talking about is if we take the length of EF, which is this side up here highlighted yellow, divided by the length of DF, this will be equivalent to the other two ratios using the same sides in the other triangles. This is the foundation, the basis of trigonometry. So this side over here would be YZ over XZ, right? These ratios are going to be equivalent to each other because we're using corresponding sides. EF corresponds with YZ, DF corresponds with XZ. And then it's also going to be equivalent in this other triangle, again, because they're all similar to each other. Let's see, it'll be BC, that's our yellow side, over AC, right? All of these ratios are equivalent. And you can imagine we only use these two sides. We could create some other ratios in there as well. I'm not going to write out a bunch more ratios using these triangles, but this is the basic idea, that all the ratios will be equivalent as long as we use corresponding sides. Now, that takes us to the really important idea, the trigonometric ratios. What we were actually doing up there was what's going to be called the sine ratio. So we have some particular names for the ratios. We have what's called the sine ratio, the cosine ratio, and the tangent ratio. And I am going to go through all these. We do abbreviate them. We abbreviate them. Sine abbreviates SIN, cosine abbreviates COS, and tangent abbreviates TAN. Those are going to be the buttons that we'll see on our calculator that we do end up using, and also the way that we write them out, in a shortened manner. So anyway, the sine of a particular angle is the ratio of the length of the leg opposite that angle divided by the length of the hypotenuse. That's a mouthful here. So let's take a look at this example triangle that we have. And for reference, for this problem, I'm going to only be looking at angle A, but we could also look at angle B as well. So the sine of angle A is the ratio of the leg that is opposite of it. So if we go across here, right, A is the side that's opposite, the leg that is opposite, divided by the hypotenuse. The hypotenuse is always across from the right angle. So the sine of angle A is A over C. It's this side length divided by that side length. Now, for reference, if we're referring to angle B rather than angle A, this does change things up a little bit, right? The side that is opposite of angle B is actually side B divided by the hypotenuse, C, right? So let's go through that. Sine of A is opposite leg over hypotenuse, which was A over C, right? A over hypotenuse C. Sine of B is opposite B over hypotenuse C, right? So it changes a little bit depending on which angle we do the sine ratio for, but we still use the opposite over the hypotenuse. Let's go ahead and look through cosine as well. So cosine of an angle is the ratio of the length of the adjacent leg. Adjacent means next to, so the adjacent leg divided by the hypotenuse. So cosine of A is the adjacent leg. So the leg that is next to or touching angle A, right? So this right over here, that's B, side B, divided by the hypotenuse, C. So cosine A is equal to B over C, adjacent over hypotenuse. Now, things do change just a little bit when we talk about the other angle, right? Because we can do the cosine of this other angle as well. So cosine for this angle is the adjacent leg, which has changed now. Adjacent is a different side. It's next to it over here. This is our adjacent leg, A, divided by the hypotenuse. So it's A over C. So cosine of angle B is A over C. So something that's really important for us to notice here, as we looked at both sine and cosine there, is depending on which angle in the right triangle you use, some things change a little bit, right? The side that is adjacent or the side that is opposite is changing locations a little bit, and we have to pay careful attention to that. Now, one thing I will mention right now to get it out of the way, we never take the cosine or sine or any trig ratio of the right angle. So we won't ever use, in this case, angle C. Yeah, we just don't do that. We don't do cosines and sines of 90-degree angles in geometry. All right, and then the last one is the tangent ratio. And the tangent uses a different combination of sides. Tangent is the ratio of the leg opposite divided by the leg that's adjacent. So opposite over adjacent. Again, some of these things are going to change a little bit. So tangent of A, of angle A, is opposite, so that's side A, divided by adjacent, side B. So A over B. Tangent of angle B, right here's angle B, is still opposite over adjacent, but things have switched a little bit. Opposite is now here, side B, and adjacent is now side A, so B over A. B over A. One of the important things that we're going to focus on here is making sure we can identify accurately and quickly which side is the opposite leg, which side is the adjacent leg, and which side is the hypotenuse. So that's what I'm going to go through here really quick. There is a nice kind of summation of this information here that we'll get into in just a second, kind of a mnemonic device, something to help you remember this. So this is what it is. It's called SOHCAHTOA. This is kind of a summary of the different ratios and what they are. So means that the sine ratio is the opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse. And the tangent is the opposite over the adjacent. So it's kind of a nice mnemonic device for helping you remember there. And then here is a diagram to sort of also summarize some of that information. So the angle that we're looking at is this highlighted one. And the names of the sides are listed here on our triangle. So I think you'll notice the opposite side is across the triangle from that angle. So it's opposite of it, it's the opposite side. The adjacent is the leg that is next to, because adjacent means next to. And then the hypotenuse is always the longest side. It's always across from the right angle. So there we go. Now, changing the location of the angle does switch things around a little bit. You'll notice how the opposite and adjacent here actually switch places, because now when we're looking at this angle, the leg that is opposite is down here, right? That's the leg that's now across from it. And the leg that is adjacent is this one here on the left side. The only side that remains unaffected is the hypotenuse. That's the one that's always there. All right, let's go ahead and go through this one example, and then we'll break part one. So we're going to be identifying the opposite, adjacent, and hypotenuse. So in order to accurately do this, we do need to pick an angle as the angle that we're using, because otherwise some of these things can change locations. So let's talk about angle C for this example. So the angle C, the opposite side here is going to be across the triangle from angle C. That's the side over here. So this one is the opposite leg. The adjacent leg is going to be right down here. It's going to be this side 30 or side BC. This is the adjacent. And that leaves one side remaining, the hypotenuse. The hypotenuse is always the hypotenuse, but it's across from this right angle right here. So if we go across from that, this one here is the hypotenuse. Hypotenuse. Now, things would change a little bit, right? If we do, instead of using angle C, if we switch things and did angle A, the hypotenuse would remain here, but now this side down here would be our opposite, and this side over here would be the adjacent. So actually the only thing that changes is the opposite and adjacent switch locations. Last one here, let's pick one of these angles. Let's say we're going to do angle X. Angle X will be the one we use it from. Feel free to pause and kind of work ahead of me if you want to, but angle X, here's our angle. If we go across the triangle from that side, or that angle, we'll find this side here. This is our opposite. Just going to abbreviate that. And then the leg that is adjacent, the leg that is next to it, touching the angle, is right here at the 21. And then leaving the last one, our hypotenuse, which is across from the right angle. All right, and that will be the end of part 1 here.